v squared plus a half of v squared. So that looks like 3/2 v squared. And then, what can we do here? Here we have a common RG, don't we? A common RG, and, oh, hold it. Yeah, a common R we can pull out, and a G.
We can also pull out a negative and make an equation after that, I suppose, so we don't have a
Okay.
segment.
Okay. You know what I'm going to do? It's easy to screw it up. I'm just going to go ahead and write it out. Okay, plus, as I see it over there, actually becomes negative, as you said, 2RG sine theta, negative, minus RG cosine theta, and then plus RG. And that sum must equal 0. Double check my work, because I do make mistakes, sometimes intentionally and more frequently not intentionally. Okay? So then, let's see, what were we trying to figure out? V, when the rod happens to be horizontal, and then these other things, V max, etc., and theta max. Okay, so let's see what we have here. If we set this up for V squared, then we'd have V squared is going to be equal to 2/3 of this material taken to the other side of the equation. And if I pull out RG while I'm at it, while I take these to the other side of the equation, then I see that I have a positive 2 sine theta, a plus cos theta, and then plus 1. Is that right?
Would it be minus?
Minus 1.
Minus one, thank you.
Well, we subtracted it on the other side.
Is that correct? Okay. Now I want to check one thing in my work. I'm going to move RG over to the other side. V squared over RG. 2/3. I want to just pause for a second, and I think I printed out the solution manual's result on this, and I just want to check and see if we're in agreement at this point before we spend more time on it. Yep, we're looking good so far. Okay. So, how do we find V when the rod is horizontal? V when the rod's horizontal.
That'd be theta would be pi over 4.
45 degrees.
Okay, you go back and look at the geometry, and it looks like because of the symmetry on both of these being at lever arm R off the center, that this rod will be horizontal when theta is 45 degrees, or pi over 4. Okay, so we're looking for theta being pi over 4 in here, and we'll then solve that for the velocity. So the velocity then would be equal to when theta is pi over 4 is going to be, I'm going to bring the 2RG back over, and then we're going to get 2 radical 2 over 2 plus radical 2 over 2 minus 1. And did they give us radius values?
No.
Okay. We'll just leave RG in the problem then. So we have 3 radical 2 over 2 minus 1.
We need a square root on all of that because you have.
Oh yes, thank you.
Square.
Yep, got a big square root coming on that. Yep. Thank you. So if somebody, actually I'm just going to go ahead and write down what the book or what the solution indicated here. That result this expression right up here, they wrote down when you are at theta equals 45 degrees, they wrote that value down as 0.748. And then when we did the square root down here, they get an approximate speed of 0.865 of RG. So that's the speed at theta equals pi over 4 radians.
That'd be 0.865 times the square root of RG.
Thank you, square root of RG. Yep. You guys are wide awake today. Okay. Everybody with me so far? Feel good? Not too bad? It's not hard writing these equations usually. You just got to be very careful about the geometry. Okay. Next, Vmax. We're looking for the maximum speed as this mechanism rocks. Vmax. So how would we find maximum speed?
Oh, we graph that and find the maximum.
We could differentiate this. And do we have to solve for V first and then differentiate? No. Just not necessarily. All we need to do is differentiate this with respect to theta, the variable expressed here, and set that differentiation equal to 0. So we're looking for Vmax. So if we take the derivative of the V squared over GR or RG expression with respect to theta, we're going to get simply 2 cosine theta minus sine theta, and so we set that equal to 0. You could bury yourself in a lot of math by finding a big old radical here and then start dealing with the derivative, but there's no need for you to worry about it. Just take this expression and differentiate that function of theta with respect to theta. And we come up with this, and the only way this could be equal to 0 is if this trigonometric factor is 0. And that should review some basic trig skills with you. How many of you aren't sure how to solve that? Means everybody's good?
Not by n.
Yeah. A quick two-step, just like dancing.
Well, you add sine on the side, divide it by cosine, you get tangent.
Yeah. Okay. Watch out. Those things show up all the time. Okay. Kick that sine over to the other side. Divide both sides by cosine, and so you're getting tan theta is 2.
Well, what's theta?
Well, then you go inverse tan at that point.
Okay.
Okay. There you
I
go.
thought you meant solving for
Okay.
2 from there. Wow, how do you do that?
Yeah. So the theta value at which this is going to occur is going to be then the inverse tan,
It's about 63 degrees.
about 63 degrees, roughly.
Well,
Now, they were asking for the speed. So what you're going to do is come back and you're going to drop in that theta reading into this equation for calculating then your speed. Now, I want to take a moment to, how are we doing time-wise? We're doing okay. What I want to do is I want to review something with you. If we said this is that particular theta reading whose tangent, that particular theta reading whose tangent was given to us as 2, then that means opposite over adjacent, right? At the particular theta reading for the Vmax. Then that means this is square root of 5. That means that the sine of theta then is going to be 2 over radical 5. The cosine of theta is going to be 1 over radical 5 when the tangent happens to be 2. So you come back to that expression then for v squared, and so v squared was equal to 2/3 of GR times twice the sine reading plus the cosine reading minus 1. So here's an exact expression for the square of the velocity. And this is which velocity now? Maximum. So this is V max's velocity squared. Exactly. Not approximately. And so V max then is going to be equal to the square root of 2/3 of GR times 5 over radical 5. Well, 5 over radical 5 is what? That's rad 5. Minus 1. Right there. If you punch that out, that should be 0.908 square root of 908 square root of GR. Last part of the problem asked for theta max. How far does this mechanism swing before it stops and starts to oscillate back and forth? It's going to go back to what position eventually? It's going to go to some theta max. It's going to go back to its
Where it started, if there's
original
no
position,
friction.
mathematically. Okay. And then it'll just sit there and oscillate between the initial position and this theta max that we need to find. So how do we find theta max? Come back and look at this. We're looking for theta max.
Set the velocity to 0.
Set the velocity equal to 0, right?
It's where it
Set the
stops.
velocity.
Well, I
Any
just said it's where it stops.
Yeah, where it stops, okay. So velocity equals 0, disappears this term. And so then it looks like all we'd be doing is solving for this trig factor right here equaling 0. Okay, so let me find some new space on the board here. I'm going to erase the stuff at the top. So theta max, this implies V goes to 0, which implies that we get 2 sine of theta plus cosine of theta minus 1 must be 0. Now, we might have a little more fun in solving this one analytically. Oh, let's play with it for just a second, just because it's good to play with trig just to keep your skills up. If we kick that over, any ideas on how to do this closed form? Closed form means with pencil paper and not your computer or calculator system.
Well, 1/2 minus half a cosine is very trig looking.
Okay. Right? Which might not be a bad idea. There's different ways you could go at it. I was thinking of squaring both sides.
Oh, yeah, that's that. Yeah, let's do that instead.
No, I like what you were saying. Very good thought. The reason is there's something here that should look a little familiar.
It's an angle.
Sine squared.
Okay, so what I want to do, this course is not just about dynamics, it's about brushing up your math skills on fundamentals to make sure you can walk circles around this stuff. So if we do this, then I want to point out to you something that's kind of interesting. If we took and drew a sine wave through its typical 2 pi cycle. Imagine that you squared these values. You square 1 and it stays 1. You square 0 and stays 0. You square 0, stays 0. Square -1 becomes 1. Square 0. Okay? Get these points. Now, if you start squaring numbers near 0, like let's say that's a 10th tall right there. A 10th squared is dramatically different than a 10th. However, what if you squared 0.9, the height close to this? 0.9 squared is 0.81. So values, the squaring of values near 1 here stay near 1. Values near 0 here diverge considerably from this. So this is just a little memory aid. So the graph you get looks like this. And that reminds us of a upside down cosine wave that has been lifted up a half and has an amplitude of a half with a period of pi. So that graph, solid graph right there, would be an upside down 1/2 amplitude cosine wave with a period cut in half, which forces it to be this, and then that whole graph is then lifted up a half. And you get 1 minus the cosine of twice, I'm going to call this x instead of theta, over 2. And that's equal to the square of the sine of x. That's how I remember that identity. And I don't have to rework it out every time. I just visualize the shape of the curves. The other one is interesting too, is the square of cosine. Can be thought of the same way. Now, the reason I wanted to get to this guy is because that fits this structure you see right here. So, this angle that sits there really means that, let's see, which way do we want to kick that?
So we're trying to sine theta divided by 2 squared.
Yeah, so we have to solve this equation. So this thing would be equal to the sine squared of what? This theta over 2, right? Looking at the pattern. Okay, and so we're saying that sine theta is equal to the sine squared of theta over 2. Now that doesn't sound so nice either.
No, it's
Okay, so let's drop back to one other thing you should remember. The sine of twice x is twice sine x cos x. So that means then that the sine of, if this is theta, then this would be the same as twice sine of theta over 2 cos of theta over 2. And if I pop that in there, I now have twice sine of theta over 2 cos of theta over 2. And if I bring the sine squared back to the other side, I could then factor out a sine theta over 2. So we're just having fun here. Just humor me. 2 cos theta over 2 minus a sine theta over 2 equals 0. This is the kind of stuff that gets you good at trig.
2 cosine, I'll do theta, is a sine above.
So you can answer this question right here first. Sine of theta over 2 equaling 0 you know that theta over 2 must be equal to 0, pi, 2 pi, etc., which means that theta is 0 or 2 pi. Okay? And what are we doing?
I'm trying to find the maximum theta.
Max theta.
Yeah, we're trying to figure out what values of theta will yield the maximum
Velocity.
position
Right.
when the velocity comes to 0 again, right? Theta max. So this says at 0, you're at a 0 velocity. Okay?
Fancy that.
Which fit our initial condition. Okay? Trivial initial condition. This other one fits the pattern of a problem we solved earlier. Because if you set this factor equal to 0, kick the sign to the other side, you're going to pick up a tangent again. But this time the tangent of theta over 2 is equal to 2, right? And so theta over 2, the theta value, when you solve your inverse tan there, is going to be, you have to then take twice the inverse tan of 2.
Double 63 degrees.
So about 127.
And you get what?
127 degrees.
Whoa.
That's right. Yeah, that's right.
According to the book, that's right.
127 degrees? That thing kicks that far?
Well, it makes
Yeah, well, the heavier ball is still lower than where it started, so
Okay, so
And
it's always good.
plausible.
you could go even further.
Always good to come back and look at the picture. So they said 127 degrees, which means the big ball gets down to here, it looks like, right? So there's your 127 degrees on that guy, and then the other one's going to be sitting up here. Oh, okay, that doesn't seem unreasonable then, does it?
No.
Okay.